This is Joanna Rutkowska of Invisible Things Lab and QTOS. It's all yours.
Okay, so obviously personal computers like laptops and phones are becoming extensions of our brains, and soon this will not be metaphorical, maybe will be more also in less metaphorical sense. However, what bothers me and many people is that even though these personal computers are becoming extensions of our brains, they are insecure and untrustworthy. And here a little digression. The adjective trusted is there are three adjectives related to trust that I wanted to quickly make sure that we understand in a similar way. So when I say something is trusted, it means that the security of the system relies on this element, meaning that this element, if malfunctions, if goes malicious, can compromise the whole security of the whole system. Meaning we don't really like trusted things. If something is secure, for me it means that it's basically difficult to attack. Yet something can be secure. So for example, it doesn't have buffer overflows. So something can be secure, but still can be spying on the user, right? And finally, we have something that can be trustworthy, meaning somehow not harmful to the user or the owner. Of course, trustworthiness implies security. However, security alone does not guarantee trustworthiness, of course. Because again, a backdoor or a rootkit can be very securely written, meaning its operator can only connect to the rootkit and get leaked information. However, it might still be spying on the user because it's a rootkit. So just the fact that something is secure doesn't mean it's trustworthy. Okay, so obviously lots of work has been done, especially in the open source community, on making things secure and trustworthy, especially on the application level, like GPG and Tor, SSH, you name it, dozens of projects. Also, some work has been done on operating system level. Among these is a CubesOS project I started 6 years ago. But when we go to hardware level, there's a very few projects where we're trying, or very little effort to build something that would be secure and trustworthy. And ironically, without secure foundation, everything else, everything up the stack is mostly meaningless if we cannot rely on the foundations, of course. So what's wrong with the x86 laptops that we all have and on which I focus this presentation? Obviously, most of the people in this room recognize this high-level diagram of a typical modern x86 client platform. A central piece is the processor package that integrates the GPU and CPU and memory controller and a number of other devices. Specifically, there's also a device called management engine. As well as essentially something that used to be called Southbridge and others. So if we now start asking questions about security of such a system, we start with obviously with boot security, which we already had a good presentation about earlier. So boot security might mean different things to different people, but different groups of users, but basically it's about how to make sure, or what can we reason about the software that has been booted on this platform. Somehow related question is how well does the particular the particular computer system, how well it deals with potentially malicious peripherals. For example, on this picture here, I might not necessarily want to, for example, for the Wi-Fi device to be trusted. Meaning, I don't necessarily want that the Wi-Fi device to be part of the TCB, that if the Wi-Fi device is malicious, that the whole security is lost, right? Sure, Wi-Fi, it would be nice even if it was not malicious, but maybe I don't want this to be a security critical element. So if we now, again, think about boot security, we obviously should start from looking at the SPA flash, which people here call a spy flash, which I like very much. So it obviously provides the reset vector, as well as a few other firmware for, especially for the management engine. But there are also other firmwares. For example, embedded controller firmware, as we just saw in the previous presentations, and other things like the hard disk would have its own firmware, Wi-Fi device typically. So this SPA flash device is a little microcontroller, of course, as you all know. By the way, one digression. The MERF, of course, one of these pins here is write protect pin, and if we ground it, then the SPA flash should not allow writing to any of the flash partitions. But we should realize that grounding this pin is mere asking the microcontroller to behave in that way. If the SPA flash has been maliciously modified, for example, by the vendor that is in our supply chain, then it might just ignore it, obviously. So we can really trivially imagine a modified SPA flash that, upon getting certain magic commands with magic parameters, will enter a state which will ignore a write protect signal, and then would allow whoever currently got root on the application processor, as you call it, reflash the static root of trust. So the whole static root of trust on this behavior of SPA flash looks quite questionable to me, especially that who are the vendors of these little flashes? These are probably some unknown little companies, often from different countries, and performing such an attack as to provide backdoored SPA flash controllers is really feasible, and it's really simple to manufacture, to do. Anyway, so yeah, that was this comment about it. And another concern is, now let me back up a little bit. So all the other devices, they either fetch firmware from the same SPA flash device, like, for example, management engine that I will mention in a moment some more about, or the other devices would have something similar, either built inside them as part of their own microcontrollers, or would be using another SPA flash on the motherboard. So another interesting question is, can we reliably upload our own firmware? And here I'm talking, will the device really honor what I will provide them? or maybe they will just say, yes, of course, I just accepted your firmware, but it will nevertheless execute its own firmware, and subsequently will be lying to me when I ask it to dump the firmware. Such attacks are also simple to implement by the hardware manufacturer. So there are these technologies, TPM, TXT, and UEFI Secure Boot, out of which actually TXT sounds, in theory at least, like it could solve some of these problems. How many of you are familiar with how TXT works? Okay, so Intel TXT it's quite old technology. It was introduced around 2006, maybe in Intel processors, and it's a dynamic root of trust, meaning that there is a special CPU instruction called senter. Actually, there are more instructions, but this is the central instruction. And once you execute senter, it takes a blob. It locks this blob in memory, so nobody can modify it, including DMA. And then it hashes it, and once it hashes it, it extends special PCR registers in TPM, the PCR 17 and up, and then transfers execution to it, meaning that it promises you to start a new, what they call MLE, measured launch environment, from a potentially compromised operating system. So you can have potentially compromised BIOS and the kernel. Then you do center, you do secure launch, and you can end up in a clean environment, which is a very attractive proposition. However, in practice, it doesn't really work. So together with my team, we have shown 3 different attacks on this, each attack completely bypassing this over the previous years. UEFI Secure Boot, probably most of you don't like UEFI, and for a good reason. It's so let's skip that. So the bottom line of this is that if we have this platform which has this many different devices, each requiring their own firmware from either the central SPI flash chip or some other SPI flashes, maybe internal, we don't really have good mechanism today to ensure secure boot, meaning to make sure that they boot firmware that we want them to boot. And I don't want to go into details whether we means the vendor or we means the user. It's I'm looking at this from the security point of view, not from the open source rights point of view. So secure boot or lack thereof is one problem, and Intel Management Engine is another problem that we face on x86. So this device that is in the processor package is the management engine, as most of you know. I had a slide. Okay, I'll show you this in a moment. So I see 2 problems with Intel Management Engine. Maybe is there any person who has never heard about Intel Management Engine here? Okay, so most of you heard. So I'm sorry. I see 2 primary problems with Intel Management Engine. One is obviously backdooring and rootkitting infrastructure. But the other problem often overlooked is what I call zombification of personal general purpose computing. So backdooring and rootkitting infrastructure, this is pretty obvious. This management engine device has full access to host DRAM It has also access to SPA flash. As we just discussed, it not only wants to read it, because, well, read it is obviously it wants to get its own firmware and to boot itself, but it also wants to write access there. And it also has, apparently it has access to CPU, some private interface to CPU. I have no idea what it can do with that. Whether it's just controlling of the power states, or can it be also control of the registers? I don't know. It most likely also has a private channel to GPU, and not sure about the Wi-Fi. The Wi-Fi probably not, but internal LAN, I'm sure it has.
It has separated pins to the Wi-Fi card if it's Intel. It has separated.
If it's Intel Wi-Fi, it has a private channel to the Wi-Fi. Yeah, that's what you're saying. Okay, whatever. So let's have the discussion at the end of the presentation. As you can see, a number of because some years ago, like many years ago, I used to be researcher specializing in stealth malware, rootkits and stuff. When I look at ME, it just makes an ideal infrastructure for writing rootkits, and this is pretty obvious. So that's one problem, and to make it worse is that even if Intel puts something there, there's really no chances for anybody outside to find out. You might say, okay, but it fetches firmware from the SPA flash, so maybe we can analyze it. But there are two catches with that. First catch is that it still boots itself from the internal ROM, read-only memory, that is in the processor package. We don't know how large it is and what code is really in this internal ROM. And of course, there is no way for us, mere mortal ones, to read this internal ROM. But assuming the internal ROM doesn't do anything evil, it's still and then assuming that any kind of rootkit would be in the SPA flash, it's still and assuming it could not be, it was not encrypted, it still doesn't provide a convenient way to analyze what they do, because we don't really know any details of the architecture or the environment, like MMIO registers and all the environment of the microcontroller on which ME runs on. So even though we could see the binary blob on the SPA flash, we can't really interpret it, what it does. We cannot run it in an emulator. IDA doesn't have support for it, and so it really looks very opaque to any researcher. Another problem with ME is what I call zombification. So this is the traditional picture of the general purpose computing, where we have operating system and then lots of logic in the applications. And this is a healthy, normal picture. And this is the picture with ME, where if you look Intel materials about how they envision ME or the use of ME, they suggest they would like to move more and more functionality into ME, because they believe this is the most secure operating system. So we can imagine that in 10 years, maybe everything, all the logic would be executing in ME. Email decryption, ME. Your all sensitive data operations inside ME. So at the end of the day, your applications layer would be mere GUI providers, and all the logic would be executing in this ME chip that we cannot know what really is what it's really running. So that will be essentially the end of the general purpose computing for client platforms, which would be quite pessimistic. These are a bunch of rhetoric questions for which the answer is no. Sadly, for a number of years, I believed that ME could be somehow constrained using VTD. VTD is the IMMU technology, which can be used to filter DMA requests from devices. So I believed a picture in which ME engine was behind the DMA remapping unit. So I believed that by reprogramming this DMA remapping unit, we could cut off ME from being able to access to the host memory. Turn out this is not the case. There was a recent book by one of the ME architects, which was published last year, and it made it clear that DMA translation doesn't apply to ME engine. So VTD doesn't work, and TXT doesn't work either. So we see problem number one with x86 is lack of reliable secure boot or verified boot. Neither any reliable way to dump the firmware from all these devices in a reliable way and analyze what's there. And number two is this unremovable management engine that we need to live with, that can spy on all the memory content, leak it out whenever it wants. It doesn't need to leak it out over networking. All it can do, it can sniff the disk decryption pass key or passphrase and just store it on the SPI partition, for example, for which it has write access. And then whoever steals your laptop or confiscates it, depending who is in your thread model, just has the disk decryption key on the SPI partition and can just readily decrypt your laptop. This is really simple to implement for somebody who writes a rootkit for ME. So one solution to this problem and others that I'm proposing here is to realize that we can improve the situation by considering state as something undesirable, and state here understood as all these elements, all these flashes on the motherboard, they carry state, persistent state. They carry firmware, right? But the firmware is a state. So let's imagine that we could implement clean separation of state. So instead of having this messy picture where we have a motherboard and these red-like rectangles represent flashes, and flashes intermixed with data, so persistent state, which again can be used to persist malware, can be used to steal secrets by malware that got root and got some secrets. They can store it there, like your disk decryption key. They can also be used as a personal identifiable information, so can compromise your privacy, anonymity. So let's imagine we could turn that picture into this picture, and this picture differs by the motherboard not having any state carrying elements, read any flash chips, and instead we introduced a separate element, a trusted stick, let's call it that way, which is a trusted device, so security critical, but very simple, which contains all this state, and it will be connected. It will be a little device like this one, right, that I'm carrying with me, and I plug it in, and it exposes now all the state to the platform. And suddenly this way we achieve several properties. First of all, this device can be, this trusted stick can be easily implemented in FPGA, for example, and we can trivially ensure that it's going to be a read-only device, right? So this way, we suddenly no longer need to worry about firmware modification attacks against firmware persisting malware. Also, we are not giving places to store stolen secrets for malware that might just happen to get to the platform through the internet, for example. We also got reliable way to verify firmware, because we can just take the stick and plug it into our trusted laptop. Our IT admin can do it and just dump it radially, right? DD even, and just compare it. Reliable. Also, we are gaining reliable way to choose what firmware we have, because we're gonna design this FPGA so it allows us to, in a reliable way, to upload firmware to store there. We can easily imagine that this device has a little switch here that you, like write protect switch, that we can, for the update procedure, we move the switch, plug it into IT admin laptop, DD new firmware, then we move the switch back, and then we use it for our laptop. We'd always see it as read-only. And then we can have several such sticks with different firmwares, different operating systems, different applications for different users, when we can trivially switch the roles of a laptop without fearing that one role will compromise the laptop, and so subsequently any other role, use of this laptop would not be safe for any other role. For example, I might switch it between my work laptop and my personal laptop. I'm leaving my work, I'm just switching the stick. So we would need some modifications to the motherboard to implement it. In the most simple variant, in step 1, all we need to do is just to move this SPI flash from the motherboard. We just move it outside. So we just route the connections, just right, ground, VCC, clock, and in meso, whatever you call it in English, in out. We just route it to a connector, and then we can plug our trusted stick there. Here we assume that the other devices would be using some ROM-like, read-only-like memory. If that's not realistic, or if we wanted more flexibility with updating firmware for the other ones, let's consider that we could build easily something I call SPI multiplexer that would expose different SPI buses to all the devices that are interested in fetching firmware from SPI flash. So at least 2, at least embedded controller, and of course our application processor. Maybe others would also be connected here. And then again, perhaps some new type of connector here. I'm not claiming this must be SPI. Maybe it would be something different. Maybe it could not be SPI multiplexer. Maybe it could just take, this is 4 wires. This is 4 wires. Among 2 are ground and VCC. So just several wires for each device, and we just here we just route all these wires, except for ground and VCC being the common ones. Okay, multiple pins, but we don't need to write our we don't need to construct our SPA multiplexer. So this way we can move all these flash elements from the motherboard and cleanly expose to one element that will be simple and we will control. We can control it. We can easily have multiple vendors provide us with this trusted stick. We can even imagine people would be able to have their own little FPGAs implementing this to make it really reliable. Another such device that might be consumer of this firmware would be could be SSD. But you might say, wait a second, why would we have disk on a stateless laptop? Isn't having a disk on a stateless laptop somehow contradictory? Well, to some extent it is, but it would be a special disk. It would be a special disk in that I'm going to discuss in a few slides from now. Because now let me say a few words about this trusted stick. It would need to have at least two kinds of storage: read-only storage for essentially code, like firmware and system, like boot and root partition, and a writable storage but encrypted for user data, think /home, and probably some key that would be also stored there. Again, the idea is that this read-only storage could be updatable only if you move a special switch on a trusted IT admin computer. Otherwise, this is all read-only for your target computer. Okay, so I finally have this slide about disk. So this could also be implemented by, this functionality could be implemented by the disk inside, at least storing the system and user data. However, we need trusted firmware for this. We need to ensure that whatever the disk, whatever writes are exposed by this disk will always be encrypted by the user key. So imagine that ME tries to leak some data, say our disk encryption key, and wants to store it on a disk. A normal disk would be happy to, if ME could talk to this device, it could ask it, dear disk, please write this bunch of data to your whatever sector. And this would look like garbage for anybody who doesn't have a secret key for this hypothetical ME backdoor. However, if the disk was also always executing encryption with the user key for which the ME doesn't have access to because it's on the trusted stick and it's not exposed by this interface, then ME could still do that. But whatever ME asked the disk to write would be stored by the disk physically, encrypted with the user key. So whoever stolen our laptop afterwards would never get access to this, would never meaningfully get access to this, whatever information ME wanted to write there. ME or SMM rootkit or whatever other malware. And as a matter of fact, I saw open source project to implement SSD controller in FPGA, which sounds like a good start for this. But this is just optional. This is step number 3 for this laptop. Any questions so far? Huh?
Who would perform the encryption for the data that you would write on the SSD? Would the trusted stick perform the encryption, or would the CPU perform?
No, it would perform the SSD here. There's a microcontroller here, of course, on SSD disk, right? Here. There's a microcontroller here. This one would be performing this encryption, and because we would provide it with trusted firmware from the stick, we would assume that it will perform this encryption correctly. ME would not be able to interfere with this process because ME would not be able to interfere with whatever firmware we are feeding to this device. Okay.
But wouldn't ME have control of the platform and be able to tell the SSD to write something via, for example, the SATA interface in the picture?
No, because that's why I said that the disk would need to run trusted firmware. That's why for the disk we would need trusted firmware. Trusted meaning that the firmware would ignore any such request from ME. Trusted firmware from the disk meaning it would be executing encryption the way we want it to do, and not listening to ME telling it, hey, don't do that. Okay.
So then, when the SSD receives a request over the SATA interface, how would it differentiate that the request came from the CPU or if the request came from the ME? If, for example, you tell it, write this data to this block.
Well, because here we assume that the SSD would be running trusted firmware, custom trusted firmware, right? There would have to be a way for telling it what key must be used for all the encryption. Okay.
I was just thinking because, I mean, so, as I understood it, I understood it, what you're saying is the ME could do a write, but it wouldn't be able to read back what it wrote because the encryption, the ME could write a block,
Sure.
but it can't read back what it wrote because that would have been encrypted by the trusted firmware.
ME, we don't care that much whether ME can read it.
Okay.
We more are concerned that somebody steals your laptop,
Yeah.
and then opens it and reads this sector from the disk,
Yeah.
and gets the decryption key and then enters
Yeah.
it and gets to your disk.
Yeah. So as I understood what you were saying, the key is that anything could write, but because it got encrypted by the trusted firmware, only someone with the key could get it back.
And
Yeah.
the trusted firmware, because it comes from here,
Yeah.
encrypting to the key that is stored here.
Yeah.
So using some interfaces, you see this, right? This is not the SATA interface.
Yeah.
Okay. So ME has no way to intercept that. We can discuss it more after the break, after the presentation. Okay, so so we saw that by doing this simple separation of state, of taking the state and moving it into one central trusted element that is simple to design and just simple to control by us, we can solve a number of problems. We can solve the problem of malware persistency, and we can have easy way to verify the firmware, and also we can, even in the presence of potential malware, especially in the ME, we can cut it off from the ways to leak the secrets stolen from the user. It's not just for ME, by the way. We also can have SMM rootkit. SMM rootkit, there were examples of SMM rootkits that were, for example, scanning all the pages, looking for signatures that look like PGP keys, PGP private keys, and once found, they would be dumping it somewhere, for example, on the disk or on the SPI partition. But still, one problem remains, and this is that such a hypothetical ME, especially ME malware, might leak this stolen information through networking, of course. So for the purpose of further slides, let me distinguish between classic malware and sophisticated malware. So classic malware would be typical malware you would get from the internet, as you can say. So you download something, maybe malicious installer, or you get your browser get exploited, whatever. This is classic malware. Sophisticated malware would be something that has much more, has fuller picture of your system, can observe the whole memory. So this is something like SMM rootkit or ME rootkit. Okay. So now let's consider several scenarios. Scenario number 0 is that we have completely air-gapped system, so not connected to the networking. That might sound like a good solution for ME not being able to leak away data, but I think somebody mentioned even today that there were examples of malware that were able to leak out data by blinking a LED using Morse code or something. You mentioned it, right? Yeah. Or you could do the same using speakers, for example. Speakers on a very high frequency, perhaps, so not to be really noticeable for most humans. So as you can see, this is not so easy. However, being able to force malware into using such channels is already quite a significant success. But for the extra paranoid, this is just a reminder that if you really want an air-gapped system, it's not necessary to just disconnect it from the network. You would need to. It would be nice to have physical switches on speakers, for example. Or another thing is that even though you might be not connecting to the network consciously, still, of course, a powerful malware that controls your platform can use your Wi-Fi or Bluetooth module to leak it out also. So physical switches, physical kill switches on these devices would be necessary for this paranoid scenario. Somehow more relaxed and more useful scenario is a closed network of trusted nodes, in which we introduce a networking proxy which is executing outside of the processor, perhaps on the embedded controller if it's powerful enough, or maybe it's a USB device that is plugged into a port and introduces itself as a networking device to the host, whatever. The point is, it's not on the host processor. And what it does, it tunnels all the networking generated on the host through some tunneling protocols, some VPN, for example, and establishes VPNs between the trusted peers. So now, even if ME on one of these nodes here decided to leak information to the outside, it cannot really leak it outside. It can only leak it to another trusted node. But trusted node, by definitions, are trusted, so it doesn't give much to the attacker. Of course, there is some corner cases here, like through modulating of the traffic, there could be some side channels. So a malicious ISP observing the traffic might just get some bits of information from it. Again, forcing attackers to using this kind of extreme measures, this kind of modulating covered channels, is kind of a success compared to what we have today, where this can be leaked anywhere without any problem by a rootkit in ME, for example. And even more relaxed scenario where we just terminate at some VPN server, or this might also be Tor exit node, in which case we only care to leave the network close to us. So we assume the adversary controls the network in the vicinity. Perhaps this is maybe one country, maybe this is right a non-democratic country, whatever, and this is the rest of the internet. So we only care about getting past that. Again, all these scenarios use this external networking proxy implemented on the motherboard or outside of the application processor. Of course, here, when I visit some website, of course, if the administrator of the website is malicious and is conspiring with the adversary, then of course, again, hypothetical ME rootkit, which has just stolen my disk decryption key, might just leak it by, for example, modifying HTTP request in such a way that in the HTTP request, there will be part of the stolen key. And then a conspiring administrator of the server would be able to get this key after several requests, for example. Again, forcing attackers, such attackers as ME, to use such extreme measures to leak out stolen information, in my opinion, is a lot of progress compared to what it can do right now, where it can just do whatever it wants. Because obviously, the problem for such a hypothetical ME rootkit is that now it can be caught red-handed, right? Because maybe the server doesn't have a conspiring admin. Maybe the server has an admin who wants to catch ME. And well, that's kind of a challenge for whoever would like to build a rootkit here, that now, if such a rootkit would need to interpose on such high-level protocols such as HTTP, for example, they really need to do it in a stealthy way, and they are really risking of being caught red-handed. But so that was about sophisticated malware who controls system in such a way that can consider doing all such attacks, such extreme attacks. What about those traditional malware? So far, I sort of implicitly assumed that whatever is on this trusted stick is not really trusted. The trusted stick is trusted, of course, to, for example, be read-only and having other features. But, for example, the BIOS image that it exposes to IP, I didn't say this BIOS image should be trusted. Because we can think, okay, it exposes BIOS image, it also exposes ME image. ME, of course, is untrusted. So maybe BIOS also can be untrusted. After all, even if BIOS turned out to be malicious, it still cannot really do anything meaningful because the stick is read-only. It cannot write back any stolen secrets. So we don't care about whether BIOS is secure or not, malicious or not, right? However, this is not entirely true, because BIOS can trivially provide escalation backdoors for the host operating system. And we don't want that trivially, for example, through SMM, right? So, and such a privileged escalation backdoor would obviously compromise the security of the host OS. And we don't want that to happen, because that would suddenly make all these attacks that try to bypass these protections. So it would suddenly allow classic malware to upgrade itself to sophisticated malware that can do all this sophisticated networking leaking. And we don't want it. We want only, if we want such sophisticated malware, we want only, for example, ME to be able to do that. Because we hope ME would not really do that, because the Intel or whoever wouldn't like to be red-handed. There's too much risk for that. However, if we suddenly opened possibility for doing such attacks to any malware, you download whatever installer from the net and it can suddenly do all that, that would be a different story. This means we care about having secure operating system running on such a stateless laptop. And as I just said, to have secure operating system, we cannot have BIOS providing trivial escalation backdoors. For example, you write XYZ to port XYZ, and suddenly you get into SMM mode. So you want BIOS without backdoors at the end of the day. Of course, somebody might say, but perhaps ME can inject something malicious to the host memory. Again, I seriously doubt ME would ever be able to do that because of the risk of being caught red-handed. Perhaps FSP could contain some triggers for some malware. Again, I seriously doubt it, because people like you who probably look at FSP very carefully would just figure out that it's just stored some blob somewhere in host memory while it shouldn't have done that. So we want BIOS without backdoors again, and thankfully we have coreboot, and which is a great candidate to do that. Okay, I didn't write my wishes for coreboot to become really good BIOS for secure host OS. And one of the missing features that we just discussed during lunch that coreboot largely misses today is support for VTD, IMMU. For example, on most systems, it does not expose DMAR tables. And DMAR tables are needed by, for example, hypervisors who would like to make use of VTD. Another thing that would be nice to have would be protection of the whole boot sequence from DMA attacks. So it would be nice if coreboot itself was setting up DMA protection as early as possible, before even it initializes host memory. I remember there was some special MSRs that could be used to set up DMA protection for memory ranges without really using VTD, because I think VTD cannot be really set up without memory being initialized, right? So that will be another wish that coreboot could implement. Finally, there's this question I asked in the morning. Like, once we have all these secure boot, for example, secure boot in a light bulb, secure boot in a laptop, or we have stateless laptop that we are so happy about being such a securely designed laptop. The question is, how do we know it actually really is a stateless laptop? Or how do I know that my light bulb, that presumably is running coreboot and all this sequence of verified boot, how do I know it's really is doing that? Maybe it's just some light bulb that doesn't really verify all this firmware. Maybe just, forgets something and then pipes it through shell or whatever. These are called I call them evil Maid attacks as a generalization of what is called evil Maid attack, which works by if you leave your traditional laptop in your hotel room and then you power it down, and the maid comes in and it plugs in a USB, boots your laptop from USB, and it installs, it infects the bootloader, so that the next time you come in and boot up your laptop and you type in your disk decryption passphrase, it stores it on some unused disk sector, and the next time attacker steals your laptop, it has the such attacks have been implemented for most disk encryption softwares. So this is a generalization in which the evil Maid doesn't really replace your bootloader, because there is no bootloader on a stateless laptop. It just replaces your laptop into a laptop that looks the same but isn't really stateless inside. It might have millions of flashes to store all the stolen information, and it might have all those Wi-Fi devices to leak it out to nearby attackers. So the question is, how do you compare two PCBs? So let's say there is a company XYZ that sells stateless laptops, and I want to order one. So I ordered it. It came through whatever company to my house, and then I open it. And how do I know it's really is stateless? I can open it. I can take a photo of the motherboard, but do we have any tools to compare it with? Because presumably the company that made it, the designer, would post detailed photos of the motherboards, maybe X-rays. Maybe I can do the same. I will take a photo. I will take an X-ray. But do we have tools that would be able to diff it? That would be nice to have, right? And just to finish, many people say, okay, so Intel is really hopeless. Maybe we should move to another architecture. And often people say, why not ARM? First of all, there is no such thing as ARM processor, of course. The ARM is just a set of IPs, right? And there are multiple manufacturers that might or might not implement exactly what ARM believes should be there. This diversity, I saw, I'm not really an ARM expert, but I saw some platforms who are dramatically differently implementing, they were implementing IOMMU in a dramatically different ways. One had something like, whatever, the IOMMU was completely different, implemented in a different way. And such a diversity makes it difficult to develop one software, one system software like Zen, for example, that would be supporting all of them equally well. You might think diversity is good for security, which is true. However, diversity makes testing more challenging, and it also makes security review more challenging. Suddenly, you have 2 or 3 combinations for IMMU, it will turn out you will have 5 different implementations of secure boot, high assurance boot, whatever it's called there. Suddenly the whole the space of possible solutions would be maybe hundreds, and you would need to figure out whether your software in all these situations really provides, your system software provides security, which is, it looks to me like it doesn't really scale that well. And finally, backdoors are still possible on ARM. It's still all these SOCs, system on chips for ARM, they are still proprietary black boxes. There's nothing that fundamentally would make such a chip more trustworthy. There's also the hope for the open source CPUs like RISC-V, which would be somehow nicer, because at least we could hope for some, maybe many different companies trying to do the same hardware, the same chips. So depending on your geopolitical situation and threat models, you would be able to choose one that you hope would not build in backdoor into the chip. But the question is about, of course, the performance, which is especially so important for personal computers that people want to use for HD movies, games, and all sorts of things that are so CPU intensive or GPU intensive. There's also a question about security technologies. Will we have IMMU on such processors? Will we have something like SGX, which is another new interesting technology on Intel, potentially a game changer? How long it will take for RISC-V to get these? When we will have a normal laptop based on RISC-V? Is it 5 years, 10 years, 20? I don't know. So these are just moving to another architecture that, as you can see, is not really going to solve any problems, at least not going to solve any problems very soon. In the time frame of 5 years, probably not. So we need some solutions for x86, because this is a dominant platform for laptops, at least. And by the way, all these evil Maid attacks still apply all here, right? This is so this clean separation of states still makes sense. And it actually also still makes sense, in my opinion, even if we move to, say, RISC-V based or ARM-based laptops. Yeah, here I just wrote again the advantages. Again, prevention of firmware infections, no places to store stolen secrets, reliable way to verify firmware, reliable way to choose firmware, so upload one and boot multiple environments and share laptops with others. Yeah, here many people after presenting this would say something like, yeah, this is a nice idea, but the market forces, like the market would never buy into this. Vendors would never change their way of manufacturing motherboards because there is no demand and stuff. So my answer to this is, for example, that not all good things for humanity must be compatible with market forces, and human rights and civil rights are one example here. And again, because personal computers, as I said at the beginning, are really extensions of our brains, in my opinion, they deserve special considerations and special protection. Because again, this is our thoughts usually. So perhaps special legislation, like especially in Europe, might be of help here. And that's all. Thank you. And now we can have questions, more questions. Actually, by the way, I wrote two kind of more thorough and technical questions on this subject. One is called Intel x86 considered harmful, and the other is called state considered harmful. So the state considered harmful is about construction of the stateless laptop, and the previous paper discusses all the problems with x86 from the security point of view.
So one of the points was that you wanted to protect the ME from observing things and writing them down.
Preventing them.
Yes. So what's to stop Intel building an ME that has internal flash? I would assume that anybody who knows where to look for the secret knows how to get it out.
Right. So here I made an assumption that I didn't really explicitly mention here, is that you can see. Sorry. Yeah, you can see all these devices might have their own private flashes, but the processor package doesn't really have flash. And indeed, as far as I know, no processor package has really any volatile, non-volatile storage. As I understand, I'm not an expert here. As I understand, the technology process for making processors would make it very expensive to have flash memory on the processor package. But of course, once Intel starts adding flash into the processor packages, that would be a problem for that.
Yeah, and they started as a flash company, so they probably have a way. They started as a flash company, so they probably know how to do it.
Again, the hope is that it would be expensive. That's my understanding is, and from talking to people who understands this technology, production technology better than I do, is that this is what prevents them from doing that. Because after all, if there wasn't any problem with that, we would already have processors with SPI flashes built in. Because generally, this is beneficial to OEMs to have as little as few chips on the motherboard as possible.
Right.
There's a question in the back here.
So I'm not yet really convinced about the preventing the leaking of secrets through the network while the machine is active. Because as I understood it, all the examples that you gave use a trusted proxy to make sure you can only communicate with trusted endpoints. But that's not really what I want to do with a personal computer, right? I want to be able to browse the internet as a whole.
No, you can. One example. So one example was this. This one. This is with trusted endpoint. But there was also an example here when you access the open network just through, say, a VPN. So what you do is basically you prevent adversary from getting the stolen data in your vicinity.
Okay.
This could also be Tor network.
But I mean, what prevents if the ME is infected in this case, what prevents it from instructing the proxy to make its own HTTP request to NSA.gov?
Oh, no, the proxy is trusted because the proxy would be outside of the processor. The proxy would be, say, part of the embedded controller.
But it allows the processor to do arbitrary HTTP requests, right? To talk to any internet endpoint. So why can't the ME just use that to talk to an evil endpoint?
Oh, as I said, it could do that. It's the only concern would be that ME could be caught red-handed doing that, and it would be not right.
But I can't really prevent it to do that, right?
You cannot. But the point is that we, as a security industry, are pretty good at monitoring networking traffic and detecting this kind of stuff. So I would expect it would be very simple for inquisitive admin to figure out that suddenly there are some suspicious HTTP requests originating from, say, this laptop, and there would be like where they are coming from. a quick investigation would show they must be coming perhaps from ME. And what would be an explanation from Intel for that? This is the only hope, that we can push them into such a situation that would be very uncomfortable for such a hypothetical backdoor to use in the wild.
Okay.
Okay. Okay, so thank you. Maybe we can discuss later.